3 is a big section. I actually break it down into 2 parts. There's 4.3 part 1, which is the Fundamental Theorem of Calculus, the setup and solving it. And then the Fundamental Theorem of Calc part 2, 4.3 part 2 is the applications of it. Alright, so this is a big theorem. Again, there's Fundamental Theorem of Calculus. Alright, and I sometimes will shorthand it to FTC. Alright, my FTC just means Fundamental Theorem of Calculus. Alright, the Fundamental Theorem of Calculus solves the area problem. It solves that definite integral, that limit of the accumulation function. Alright, so remember, we have a function that finds the limit of the Riemann sum, that's that adding up all those rectangles as the Riemann sum is, for a continuous function. So the function has to be continuous, no breaks, holes, or asymptotes, between a to b. Right, now, this just means, that's it, the function just has to be continuous over the interval. It doesn't necessarily mean it's positive, even though when we looked at areas in the previous section, that's the only case we looked at. Now we're going to broaden that concept. It doesn't necessarily have to stick with positive values. Alright? So it can be negative, and because of that, sometimes it doesn't find the area under the curve, but it has to still do with area. It has to do with the accumulated sum of the function. Alright, the formal definition of the definite integral is, if f is a continuous function between a and b, the limit of the Riemann sum, the limit of the sum of those rectangles, where x equals n is the n subintervals, where we broke it down into n intervals, where each width is the same distance. The definite integral is denoted, so it solves this limit. This is a special limit. As n goes to infinity, remember, as n goes to infinity, that change in x goes to 0. The width goes to 0. Of all of those areas, right? If we add up all of those areas, and it is an infinite sum, right? Because the delta x is going to 0. What it basically boils down to, it's the sum of all of the function values from point A to point B. Right, that's what it is. That's what this limit means. It means I'm adding up, because the change in x is going to 0. And so there are infinite limiting points between any two moments. And so we're solving for the infinite limiting values between A and B. That's what we're finding. We're finding the sum of those. And as it translates, it's adding them all up. Well, that limit is solved using a definite integral. Again, this is why this is an S symbol, because it stands for the sum. It's the sum from A to B. So A is the lower value, B is the higher value. A is the starting point, B is the stopping point of my function f of x with respect to x. And so, again, what it's doing is this is an accumulation function. This finds the sum of the function values, the f of x, the y values, from x equals a, the lower value, to x equals b, the higher value. Alright, so it's an infinite sum, right? It's adding up all of the function values. Now, again, this does not say anything about my function has to be positive, alright? So I can have positive function values and negative, and I can have either all positive or all negative, or a combination of the two. Since that's the case, we can't straight say it's the area like we did in the previous section. Right, but it does have to do with area. Basically, it's broken into 2 cases, which we're going to look at next. All right, so it has something to do with area, right, because it's the accumulation function. But there's a little more to it, because this is a broader definition. All right, so again, we want to find the definite integral, which is the solving that limit. Again, we do it without having to actually draw the rectangles and add them up or solve that limit, because again, the algebra on that is hard. And we'll get to that. It's the following theorem, right, which is the Fundamental Theorem of Calculus, solves that definite integral, that limit. Alright, so the Fundamental Theorem of Calculus can be proved. We don't do it in this class, but it can be proved. If my function's continuous, it means there is an antiderivative, exists. All continuous functions have antiderivatives. So if I can find any antiderivative, and usually we find the general one, so f of x would represent any, you can find any of them with a constant, without a constant. We typically do it without a constant because it's easier. So f of x here would represent my antiderivative. Alright, so that's taking care of the integral part. But I haven't taken care of the lower limit and the upper limit, the a and the b. Well, you do that by actually plugging those values into the antiderivative. And you plug them in specifically, the high value goes in first, And then you subtract plugging in the low value. Again, you're plugging them into the antiderivative, right? Capital F of x is the antiderivative. And so to solve that limit, it's actually a unique fact that it's the antiderivative that we use, and we solve for the difference of the antiderivative from the high value to the low value, right? It's the exact change in my antiderivative from a to b. That's what this definite integral solves for. That's what that infinite sum is equal to. The area under the curve, if it's a positive value, is equal to. Alright, so now the geometry, what the picture looks like. So this is how we solve it. So we solve it with, we find any antiderivative, we plug the high value in, and subtract plugging the low value into that antiderivative to find the exact change. And so there are two things that can happen. Two ways to look at it from a graphical point of view. Two cases. Case one is the case that we looked at in 4.2. If my function's positive and continuous, meaning I can graph it completely above the x-axis from point A to point B. Alright, then the definite integral, which again is solved using this fundamental, so this is the Fundamental Theorem of Calculus formula, finds the exact area under that integral. It's the accumulated sum, which is equal to the exact area. Alright, so the picture, we draw the picture. So suppose this is my lowercase f of x. This is the function that's graphed, right? Lowercase f of x. I start at A, I stop at B. Alright, and so my function's completely positive, right? F of x is bigger, alright, all my values from A to B are positive. When we find the definite integral, what we're doing is we're literally adding up every single every single y value of my function. And so when we take the integration of A to B of f of x, dx, in this case, it does equal the area under f of x over the interval A to B. And again, the reason why is because what we're doing is we're literally adding up all of the all of the y values, the function values, from A to B. And so when I add up every single y value, and there are infinitely many of them, right? That's all the heights of my rectangles, right? Those are my y values, and I add them all up, it gives me the area. Right? It gives me the accumulated sum of that function from A to B. That accumulated function from A to B is the area under my curve. If my function's positive, again, this is true because f of x is positive over that A to B. All right, now the other case, well, because this is a broader definition, we don't necessarily have to be positive, and so the second case is if our function's continuous. All right, just continuous, which is the original definition. It's continuous from A to B, which means my function values might be positive, might be negative, might be both. Have some positive values, have some negative values. And I'm going to graph the case where there's both, although you could be the same idea if it was all negative, then you'd add up all the negative values. All right, what it finds, again, this is still the Fundamental Thm of Calculus. You still solve the definite integral same way. Find the antiderivative, plug the high value, plug the low value. But in this case, the exact change is the difference between the area above, which we consider the positive area, and the area below, which we consider the negative area, or subtracting that area. And so the picture, if I draw a picture where I've got both positive and negative values of my function, so suppose this is my f of x. Again, remember, it's the lowercase f of x. So the graph that we graph is this function, f of x. It's inside my integral. Alright, so if that's the function, and I want to find the integration from A to B. And so we'll mark off, we'll say that's like x1 there where it crosses the x-axis. And so remember, I'm literally adding up all of my y values here. Well, my y values, my function values here are positive. Then it hits 0, and then I add up all my function values down here. Well, these function values down here, these y values are negative. And so when we find the definite integral, because it's an accumulated sum of positive and negative values, what happens is it's not area anymore, exactly. It's we'll say this is area 1, and we'll say this is area 2. What it is, it's area 1 minus area 2. Alright, that's what that So it's the difference between the positive area and the negative. So this would be the positive area. This would be the negative area, which is below my x-axis. And so what it does is it finds the net change in area. The difference between, and with this picture drawn, I would guess that this actually come out negative, right? Because it looks like there's more area below than there is above. And so you can actually get the answer to come out negative if there's more area below. You can get the answer to come out positive if there's more area above. And it actually can come out 0 as well. If you have the same amount of area above as you do below, the integration can actually come out 0. It doesn't mean the function value is 0. It means when I added up the positive part and I added up the negative part, they cancel each other out because they're the same. All right, so the accumulation sum happens to end up being 0 in that case. All right, and so what happens is well, the positive area would be my increase, right, my gains. The negative area would be my decrease, right, because my function would be negative, it would be my losses. So if this were a profit function, the first part I'm gaining profit, all right, then at x I stop gaining profit, and then from x to b, my x1 to b, I would be losing profit, right? And again, this area would give me exactly how much profit I'll lose. And we'll get into those applications later. All right, so those are the two different interpretations, and we're going to do example solving the fundamental theorem of calculus and draw the picture so you can see the difference between the different cases, the different outcomes. All right, so we'll stop there and we'll do the examples in the next set of videos.